opposite of malleable is brittle. That means it's easily cracked and broken when struck or burnt. This is peanut brittle. This is a good dessert that I really like. It's called peanut brittle because it's very brittle. You can take a hammer and smack it and it'll break into a whole bunch of pieces, kind of like a sheet of glass. A sheet of glass would be very brittle. Slate is very brittle. This is a type of rock that is used sometimes for roofing tile. So slate is a rock, and we definitely can show you some examples of this, of slate, in the classroom. It's very brittle. If I take a hammer and I smack this rock, it will definitely shatter. It'll definitely break. Very brittle. Glass, very brittle. We already mentioned this. This is something pretty obvious, I think. If I took a hammer to your glass window and smacked it, you could easily break and shatter the glass. It's not going to bend and curve and things like that. It's going to break. It's going to shatter. Here's a clip. Here is cast iron. This is very brittle. Cast iron is very brittle. This is a sign that has been broken. It's actually been cracked in half. Magnetic. You're probably familiar with things that are magnetic, with magnets. Different metals that are going to be attracted to magnets, I'm going to expect you to know this, would be iron, cobalt, or nickel. And we could do some demonstrations with magnets in the classroom. Here's a clip looking at magnets and how they behave in outer space. Pretty cool. Here's a clip.
This is Richard Garriott coming to you from the International Space Station. I'd like to talk to you about magnetism. Some people have wondered if magnets work in space. A magnet, such as I have here, creates a magnetic field that comes out of one end, goes around the object, outside of the object, and comes in the other end. And so in this case, this magnet, which acts just like a compass, will align itself with the Earth's magnetic field. And so if I release this magnet here in front of me, you can see that the magnet is now pointing this way. That's the south end of the magnet, by the way, and that's because the Space Station is headed south. We're over Australia right now. And just in the few minutes that I've been standing here working with this magnet, it's aiming farther and farther to the ground because we're getting closer and closer to the Earth's magnetic south pole. If we were traveling over Canada, you would see that the other end of this magnet would aim more towards the ground as we got closer and closer to the northern magnetic pole. Also, this is actually two magnets, and you can see that magnetic forces operate over a distance, and that the north end and south end of a magnet attract each other, whereas if I turn it around and try to put the two north ends together, you'll see that it turns the magnet over and attracts it. There we go. We can start it lined up with the Earth's magnetic field, and it will attract. Or if I start it lined up with the Earth's magnetic field but approach it with the opposite end, there you go.
Magnetite is a naturally occurring magnetic rock. Back in the old days, it was called lodestone. Here you see this picture of magnetite with what's called iron filings sticking to it. Iron filings are little pieces of iron, and it's kind of almost like sawdust, but it's sawdust that's made out of iron. Paper clips will stick to lodestone, magnetite, and here's a clip about lodestone. Solubility is another physical characteristic of matter. Solubility means that it has the ability to dissolve. in another substance. We can take a look at food coloring dissolving in water in the classroom. The solute is the thing, it's the substance that dissolves into the solution. So, for example, if I take salt and I mix it into water, the salt is going to dissolve into the water. That means the salt is going to be called the solute. It's the thing that gets dissolved. The solvent is the thing that does the dissolving. Water, in that case, was salt. Water would be the solvent. I'd take salt, the solute, put it in water, stir it up, and the salt would dissolve in the solvent. It would dissolve in water. Water is sometimes known as the universal solvent. It doesn't really mean that it dissolves everything, but it does dissolve a whole lot of stuff. So water is a very, very common solvent. A solution is the dissolved mixture of the solute and the solvent. You can get an idea of where the word solution comes from. Solute, solvent. Salt water is a solution. Sugar and water, the sugar will dissolve in the water, and so that sweet, sugary water, that would be a solution. Kool-Aid. You take Kool-Aid packet, put it in water, stir it up, dissolve it. That Kool-Aid is a solution. Here's a clip. Permanent marker. You may have heard of permanent marker. This is something we can do in the classroom, but if you write on your hand with permanent marker and then you just run water over it, it's probably not going to wash it off. So that's why it's called a permanent marker, because it does not dissolve in water. However, can it be dissolved? Well, yeah, and we'll take a look in the classroom how water does not dissolve permanent markers, but something else will. If something is insoluble, that means it cannot be dissolved in a given solvent. So, like, for example, like I just said, a permanent marker is insoluble in water. The permanent marker does not dissolve. It does not get washed away by water. Here's a picture of oil and water. When you put them together, you notice that the oil does not dissolve in the water. The oil is insoluble in water. This is gasoline. And you may have seen something like this, like when you're walking through the parking lot or maybe on your driveway. You could see this kind of like this rainbow effect. What happens is the gasoline and water on the street don't mix. The gasoline does not dissolve in the water, and so you get this film on top, and that film can refract and reflect light in weird ways and get that rainbow effect. Here you see Italian dressing. Italian dressing is vinegar down here, which has water in it, and then there's oil, so like vinegar and oil, and the oil does not mix, it does not dissolve in the vinegar, so it's actually separated into two different layers. So before you have light Italian or Italian dressing, you usually shake up the bottle before you pour it onto your salad. Grease, oil, and water, again, don't dissolve. So they don't dissolve in each other, so grease and oil will not dissolve in water. You may have heard something about if you have a grease fire. Let's say you have a pan of bacon in your kitchen and it gets real hot and it actually catches on fire. What do you do? Well, what you don't want to do is you don't want to take like a glass of water and throw it on the grease fire. That would be bad. We'll take a look at a clip and see what would happen.
You want to put that over, leave it on for 30 minutes to cool down. Turn off the stove, turn off the gas. Another method is a chopping board, be it wooden or plastic, of its oxygen that it needs to survive and sustain itself. So deflecting the flames away, protecting yourself, just like that. Leave it on the pot lid, leave it on the stove for at least half an hour. And the last method, which you can when they're damp, over your hands like that, so you're protecting your hands, protecting yourself, and the same method once again, deflecting the flames away from yourself and leaving it on. Also, another thing that we don't tell you what not to do when you have a kitchen fire. Do not do this at home. Do not do this anywhere. This is why. Okay, this is what happens when you...
Now we know some physical properties of a whole bunch of different things. So try just in your head to come up with as many physical properties for a banana as you can think of. One of the ones you probably come up with is color, like this is yellow in color, this part, but also maybe even think of the plant itself. So the leaves could be green. So go ahead and think about as many physical properties you can for bananas. Stop the tape if you have to. Let's do the same thing for a steel nail. Color, is the hardness, magnetic. You think about it as a banana magnetic. All right, now things can get a little bit tricky, so make sure you pay attention here. You might want to listen to this once or twice. Size-dependent properties. Some physical properties depend on how much that you have of a substance. And the best way to try to understand this is to think of some examples. It could be something like mass. And if you think about it, let's say I have a hunk of gold. The more gold I have, the bigger that hunk of gold, the more that it's going to weigh, the more mass that it has. The more of the gold I have, the bigger the hunk of gold that I have, the more volume, the more space it's going to take up. Those are size-dependent properties. It matters how much of the stuff I have. A size-independent property is the opposite. It's a property that it doesn't matter how much of it that you have. So if you have this much gold versus this much gold, it really doesn't matter. So some examples of size-independent properties would be this list right here. So, for example, color. If I have this much gold, I mean, it's gold in color. And if I have this much gold, it's still gold in color. So all of these things would be what's known as size-independent properties. Okay, well, that's all the time we have for today. So we'll catch you next time. See ya.